Good morning to everyone. Good afternoon, indeed. Sorry. So let me start by saying a very huge thank you to Cecilia, Fabien, and Yves. Well, first of all, for this incredibly nice 20th edition of this conference, which is very close to my heart, as I've been doing my doctorate here in Lumini. And also, well, thank you for the trust that you put in me, inviting me as a plenary speaker. It is, of course, an honor, a pleasure, and a little bit of a stress. But yeah, thank you. And thanks to all of you for being here. You know that you are, as Fabien said, you are very lucky to be here, but I'm also lucky and happy to have all of you here at my talk. So before we start with the math, since now it's started to be sort of a tradition to talk about this, what's my AGCT number? So this is my 5th AGCT in a row, and it was full of first time. So this is my first AGCT 2017 as a PhD student with Anna here. This was my first talk at AGCT 2019, where I met a very nice guy that you probably know. This was my 3rd AGCT and the first one on Zoom, hopefully the last. My 3rd AGCT 2021, the first one in which I already had a position, a permanent, sort of permanent position. And this is my first time as a plenary speaker at the AGCT. So speaking about first time, maybe this is the first time that you heard about the sum rank metric. So this talk is going to be about reproducing construction of so-called evaluation curves in the Hamming metric, a metric that you heard about in the first session of coding theory on Tuesday afternoon, in this new metric called the sum rank, which I will, of course, explain at the beginning of the talk. But let us start, so maybe just let me say that the work that I will present here are particularly based on 2 joint work with Xavier Caruso from Bordeaux, like me, so a colleague. Okay, so let us start very calmly by thinking about how would you represent messages or data that you want to send. So imagine the following real-life case. You have 2 antennas that are exchanging some flux of messages. And of course, one of the first ideas that you would have in mind when you want to put a structure on these flux of data is that you will look at them as vectors, vectors with entries in some set, or to say in a finite field. And of course, if you already attend some talks in coding theory, you know that when you are exchanging messages or when you want to store some data, eventually some errors will happen. So you may lose some piece of data, like this. And so the goal of coding theory, or at least one of the main, is to be able to encode the messages in order to detect and correct the errors that may happen. And one of the classical way of doing it is that you are going to add some piece of messages to your vector called redundancy, which is not necessary in the sense of is not part of the message that you want to send, but it will help you in be able to detect and correct the errors that will eventually happen. So in this first context, your code words, so your encoded messages, are vectors, and the errors that may happen to change your code words are vectors with few non-zero entries. And you probably already seen those codes, and those are codes in the Hamming metric. But now let us have a look at a more general picture. So imagine that now you have multiple set of antennas exchanging messages. So again, you can look at your code words or your encoded messages as vectors, right? And imagine what type of errors you could have here, okay? For instance, you could lose, at a certain time t, the piece of data of any of these code words. So you can eventually lose all the piece of data at a certain time. Or even worse, I would say, it could be that one of the antenna completely stop to work, and you lose a complete set of message here. And if you know a little bit of the code in the hemi-metric, you will know that in the first case, you will be able to correct the error, but here it's going to be almost impossible to recover your message. Another way to look at this is, instead of looking at those three messages as unlinked one, you can look at them together, put them into a matrix, and now so your code words are matrices, and the errors that may be added to your code words are matrices of small rank. And now you may want to put this in an even bigger picture. Imagine different groups of antennas exchanging messages that you are now represented as matrices, and you want to look at all of them at once and to correct errors in somewhat a linked way. So you are going to put these matrices in a vector, obtaining then a vector whose entries are matrices. So this is the type of code that we are going to work with. And now let us put a little bit of mathematical rigor here. Okay, so let's F be a finite field, and I will use the letter H for any F linear vector space, and though with a metric that I will use in the rest of the talk. So a linear code C, or F linear code C, is a F vector subspace of H. And in the rest of the talk, we will be mainly interested in the three of the main parameters of such a code, which are the dimension of the ambient space, which is called the length of your code, the dimension of your code, which is dimension as a vector subspace, and the minimum distance, which depend, of course, on the metric you put on H. And we are looking in particular at K and D, because K is linked to the quantity of data that you can encode with your code, while D is connected to the error detection and correction capacity of your code. So in principle, you will have code with K and D big. And so if you think about the first case that we look at, so where your code were vectors, then this is a case of so-called codes in Hamming metric. So here, codes are FQ vector subspace of FQ to the n, and the Hamming metric that you put here is just the metric that will count the non-zero entries of the code words. So this is probably one of the most natural way of representing data. So this metric was introduced back in the 50s. We have many constructions of such codes. They have been very well studied, and we know that those codes respect the so-called singleton bound, which is telling you that even if you would like to have codes with K and D as big as possible, well, you cannot have everything that you want, because K plus D is bounded by the length plus 1. But of course, the main characters of this talk are not such codes, but codes in the sum rank metric. So let me give you the setting in which we will work. So I will mostly work with FQ to the R, so a finite extension of the final field FQ of degree R, and I will fix S to be a positive integer. And so, as you can imagine, our code words now will need to live in the product of some matrices space. And this is actually what I'm going to do. So my H now is going to be the product of, let's say, S space of R time R matrices with coefficient in FQ. But instead of looking at it in this way, I'm going most of the time look at this space H as the product of the FQ linear endomorphism ring of FQ to the R. Of course, once you fix a basis of FQ to the R over FQ, then you get isomorphism between these spaces, which, and the rank in particular, which of course is something that we are going to be interested in, will not depend on the choice of a basis. And so we can work on the left side or on the right side without loss of generality in what follows. Okay, so let me now define what is the sum rank distance, even if I guess now you expect it to be like this. So if I take two elements in my space H, so vectors of morphism, now I'm going to define the sum rank distance as the sum of the rank, as the name says, of the difference of the morphism I appearing in my code worth. Right? So now, of course, a code C in the sum rank distance is going to be a FQ to the R linear subspace of my space H. So these S times the FQ endomorphism of FQ to the R, and with the sum rank distance. And so in particular, the length, as I told you, is going to be the dimension of the empty space. So here will be S times R. The dimension, again, is the FQ, is the dimension of C over FQ to the R. And the minimum distance is the minimum of the sum rank distance of a non-zero element in my code and the vectors whose entries are ordered zero matrices, right? And you can already see in here that if I fix R to be equal to 1, now my matrices will be scalars, and I retrieve vectors of scalars instead of vectors of matrices, and so I retrieve scores of length n or length s in the Hamming metric. While if I take s equal to 1, I'm no longer looking at vectors, but just as singular matrices, as single matrices, and so this will correspond to the in-between case that I show with the antennas, and those are so-called cos-hinder rank metrics. So you can also think about the sum rank metric as a way to include some of the metrics that we usually put in the context of codes or linear codes. And you can also think, so let me anticipate one question, that the setting in which I put myself is not the most general one. And indeed, you could imagine to not consider square matrices which all have the same size. You can even consider H to be the product of non-square matrices of different size. And this would be the most general definition and settings for the codes in the sum rank metric, but for, let's say, for lack of time and also for sake of clarity and notation, in this talk we will stick to this case, which is also the case I would say that most of the people working in this field look at. Okay, and in particular in this context, so when I'm looking at FQ to the R subspace, linear subspace, then our codes in the sum rank metric will respect exactly the same singleton bound that we have in the Hamming metric. So D plus K is bounded by N plus 1. All right, so what is the goal of this talk? As I said, in the Hamming case, we have plenty of construction, and you already met some of them. And basically, all the construction that you met during this conference, so on Tuesday afternoon, they were evaluation codes. So codes that are constructed by evaluating some objects. And so here we aim at reproduce such construction that we know very well and that perform sometimes very well in the Hamming metric in the sum rank metric. Okay, and so the codes that we want to have in the sum rank metric are the following three. So of course, if you are thinking about evaluating object, one of the first objects that you have in mind are polynomials. So we will start by univariate polynomials, which in the Hamming metric gives rise to Reed-Solomon codes. Those codes are known to be optimal. They obtain the singleton bound. They are very well known, and they are also used. But they suffer, let's say, from a small limitation that I will comment about later. They are somewhat short code. And in the Hamming metric, already people that try to construct longer codes, they went in the two following generalization of Reed-Solomon codes. So you can either evaluate multivariate polynomials, giving rise to so-called Reed-Muller codes that you saw in Gorpade and Nardi's talk on Tuesday. Or you can eventually evaluate quotients of polynomials, meaning rational function defined over an algebraic curve, giving rise to so-called algebraic geometry codes, or AG codes, which, of course, are particularly important for these conferences. They contain almost 3 out of the 4 letters of the conference. And all right, so let us start by presenting you the construction of Reed-Solomon codes. So I'm fixing k and n to integers. K is smaller than n, positive, of course. And so, as I told you, we construct Reed-Solomon codes by evaluating univariate polynomials, so p of degree bounded by k. So this is actually the construction where you evaluate a polynomial at distinct elements over fq. So you fix n of these distinct elements over fq. So you have a code which has length n, of course, by construction. The dimension of this code, well, provided that you take k smaller than n, then the evaluation map sending p to px1 up to pxn will be injective. So the dimension of your code is the dimension of the ring of polynomials that you are using to construct the code. So this will be exactly k if the degree of the polynomial is at most k minus 1. And now about the minimum distance. Well, you want to count the number of non-zero entries of your code was. Meaning, if you look at the opposite question, you want to count the number of zeros of your polynomials giving you a code was, and you want to remove this number from the total length, which is n. And you know that a polynomial which has degree at most k minus 1, which will have at most k minus 1, 0, giving you that you will have a minimum distance of at least n minus k plus 1, but you cannot have more. The singleton bounds say that you cannot have more. So this is exactly the minimum distance of your code. So those codes are optimal. And when I say that they are somewhat short, is that I defeat you to find more than q points over fq distinct. And so you cannot have Reed-Solomon code longer than q. You can eventually go up to q plus 1 if you want to add the evaluation at the point at infinity. OK. But so in any case, those codes are optimal. So how can we construct those codes in the sum-rank metric? Well, we need to find the tools, so the polynomials whose evaluation will not give you scalars, but matrices. So let us go back to the setting of sum-rank metric code. So fq to the r over fq, and I take phi to be the q Frobenius generating the Galois group of this extension. And so the object that we are going to work with for the rest of the talk in different form are so-called Ore polynomials. So the ring of such polynomials is denoted this way. So those are polynomials with coefficient in fq to the r with usual sum, and where the multiplication is twisted by phi. So t times a equal phi of a times t. And OK, now that you have these polynomials, you want to evaluate them to construct your code. And of course, the first thing that you will try to do is you evaluate them at elements in fq to the r. But be careful, you can do this, but this will not define a ring homomorphism. So just have a look at a minimal working example here. If I fix, let's say, some a in fq to the r, and I consider the polynomial t and the polynomial at, and I do the product here, by the rule, here this will be phi of a t squared. And now I'm taking also some c in fq to the r, and I evaluate these polynomials as c, meaning that I will get phi of a c squared. On the other hand, let me take t evaluated at a c, So let us write it like this. And let me take A of t evaluated as C and do the product of these two. Then this will be C times AC. So AC squared. And as soon as A is not in FQ, then those two guys are different. And indeed, what work when you want to evaluate such polynomials is to do so at phi. So you have an evaluation map sending you a polynomial P exactly to the space we were aiming for, right? And you can do a little bit more than that. You can fix an element C in FQ to the R, sending P to the evaluation of P at C phi. And you can also show that these cover all the morphism that you can use at which you can evaluate our polynomials. And now maybe you will expect what will happen. I don't want to end up here. I want to end up in some product of those spaces. So I'm going to take S distinct elements in FQ to the R, and I will send P to the vectors whose entries are PC1 of phi, PC2 of phi, up to PCS of phi, right? And now let us put this in a definition. We define so-called linearized Reed-Solomon curves to be the image under this evaluation map of the ring of our polynomial of degree bounded by a certain k. So this construction goes back to 2018, and it was proposed by Martínez-Peñas. What about the parameters of such codes? Are those codes as good as Reed-Solomon codes are in the Hamming metric? The answer is yes, but you need, as in the case of classical Reed-Solomon codes, to put some restriction. The first one that you want to put is that k, so the degree bound that you have has to be smaller than r times s, which is the length. So this is exactly the same condition that we had in the Hamming metric for Reed-Solomon codes. And you also want the CI to have pairwise distinct field norm. Under this hypothesis, then the minimum distance of your code will be exactly r times s, so the length, minus the dimension k, which once again only counts by the fact that you are evaluating univariate polynomials, so that the dimension is again, as in the previous case, plus 1. So again, those codes are optimal in the sum rank metric. Why so? Let us have a look at how do you prove that the minimum distance is this one. Well, first of all, now what we are studying is the rank of morphism which are obtained by evaluating the polynomial, say, P, at Ci times phi, okay? So this is exactly P evaluated at Ci phi. And by the nullity rank theorem, well, this boils down to the dimension of FQ to the R of FQ minus the dimension of the kernel of this morphism, right? And now you can prove that indeed, if you take another polynomial here, then the dimension of the kernel of this morphism over here will be bounded by the degree of P. So this is exactly the equivalent of saying that a polynomial of degree k cannot have more than k zeros. Same things, but for other polynomials. So you combine those two things, and you get the minimum distance. Right. But again, we need to prove this. You indeed are using the fact that the norm of the field norm of the Ci are pairwise distinct. So and since the norm lies in FQ, now you know that you cannot have S bigger than Q, actually. So you have a similar problem as for Reed-Solomon codes. Similar, not exactly the same, similar. So if you want to solve this in the sum rank metric, well, one idea will be to look at how do you solve this in the Hamming metric. And I already spoiled you a little bit this. One way is going to be to try to construct the equivalent of Reed-Muller codes. So here, as I told you, those codes are constructed by changing from univariate to multivariate polynomials. So you take polynomials in the variable s1 up to, say, x to the m, and you evaluate those polynomials at all the points of fq to the m. So you get codes over fq, which are of length q to the m. The parameters, I'm not going to give them explicitly here. They are not as good as the one that you can get with univariate polynomials, so they are not longer optimal. But those codes are quite long, that's for sure. So if you want to mimic this in the sum rank metric, what would you do? Well, of course, you will go from univariate Ore polynomial to multivariate Ore polynomials. And indeed, this is exactly what we are going to do. So we are going to consider now this ring of multivariate Ore polynomials. I'm in the same settings as before, fq to the r, extension of fq, phi is the Frobenius, and I'm also fixing m tuple of integer e1 up to em. And so this ring is, again, a ring of polynomials with usual sum. You take the variable xi to commute, and then again you have the multiplication by scalar, which is twisted by phi. So in particular, for xi, you will have that xi times a is phi to the power ei of a times xi. So if you want to use this ring to construct Reed-Muller codes in the sum rank metric, what do you need? Well, first thing, you will need an evaluation map, which will send you a multivariate Ore polynomials to the codomain that we are interested in, so to matrices. And once you have that, then if you want to study the minimum distance, of course, you also want a bound on the dimension of the kernel of the morphism that you obtain when applying this evaluation to a polynomial P. So that's the two things that I want if I want to get Reed-Muller codes in the sum rank metric. And so, of course, I already convinced you that evaluating Ore polynomials at elements of fq to the r will not work. So you may expect now that we are going to evaluate those polynomials in multiple of phi to the power ei. Probably that would be the most obvious answer. And we are not going to do that, but quite similar thing. So another feature of the evaluation of Ore polynomials is that when you restrict the evaluation to the center of this ring, of this algebra, so to polynomials which commutes with all the others, well, then you should get a ring homomorphism to the center of the algebra of matrices, which is your field. So in our case, which is fq to the r. So what you do when you're looking for evaluation here is that you are going to look for something that respects these things. So something that when you apply to the center of the algebra will give you evaluation which are scalars. And so the right way of doing it is you consider function gamma that go from z to the m. M is the number of variables that we fix into fq to the r, which respect this condition, which I will not read loud, but which concern also phi, and that some of you may recognize. We can talk about it later. And you will send the multivariate polynomials to more or less what you were expecting. So you will evaluate xi at phi to the power ei. So that's exactly what I have here. Okay, so every variable x1 to the power u1 is evaluated at phi to the power e1. But I'm also adding this element in fq to the r coming from this function gamma. So gamma of u will be an element which lives in fq to the r. So this defines an evaluation which performed well with respect to what I told you before. So now, if I take the set of all the convenient gamma respecting these rules over there, then I can define a multi-evaluation map sending P to this epsilon gamma P for gamma running through all the convenient ones. Once I have this, of course, the definition of the Reed-Muller codes in the Summer metric is done, in the sense that you define those codes to be the image under this evaluation map of the multivariate or polynomial rings of degree bounded by the certain integral. This is exactly the same story. What about the dimension, what about the minimum distance of those codes? Well, you need to obtain a bound on the kernel of those morphisms here. And this is quite similar to what you get for the, well, in the non-ORE case, so in the classical case. So we have a bound on the sum of the dimension of the kernel of these maps, which is, so it's bounded by the extension degree times the degree of the polynomials times q minus 1 to the power of m minus 1. So you may recognize something here, because the way of proving it is basically using the classical result that you have on the order of vanishing at a certain elements in fq to the m of multivariate classical polynomials. And what we are using here is, so this first ingredient is the reduced norm of ORE polynomials. So this is, so the reduced norm here is the equivalent of the determinant map for matrices. So it's something that will bring something from your algebra, from your ring, to its center. So in our case, the reduced norm of P will be a classical multivariate polynomials. And so once you are able to prove this bound on the dimension of the kernel of your epsilon gamma P, then you just need to relate the order of vanishing of your classical polynomial at gamma with the order of vanishing of your classical polynomials at elements in FQ, and then you just apply this bound. So that's a sketch. Of course, there are a lot of technical details hiding here, but those are just two main ingredients, the evaluation and the bound. Once you have that, then you can study the parameters of your linearized Reed-Muller codes, the length, and the only things that you need furthermore is to know how many convenient H you have. And so you will have that the cardinality of H is q minus 1 to the m. And so with these two things, this bound and this cardinality, you have the length is r times q minus 1 to the m. The dimension is, as usual, nothing but the dimension of ring of multivariate polynomials in m variables and degree at most c. And the minimum distance now is exactly come from applying this bound over here. OK. But now, so this was for the multivariate case. And now let us go a little bit more further and use some algebraic geometry tools. I think this is why also we are here. So again, I want to generalize the construction of Reed-Solomon codes, which is again here. So I'm evaluating univariate polynomials at elements over FQ. What I want to do is the following things. Instead of evaluating at FQ, at elements over FQ, I want to evaluate at rational points on an algebraic curve. So to do so, I need to find out what are the objects that I can evaluate at the points on a curve. So this will turn out to be rational function on my curve. But I also need, if I want to construct a linear code, to have a structure of a vector space. This is exactly given by the so-called Riemann-Roch space of a curve. So let me give you a little bit of settings. So here, X will be a nice curve whose definition was given by Kedlaya in his talk yesterday. Nice curve. And I will take some rational points on my curve, P1 up to Pn. And the function that I'm going to use lives in the so-called Riemann-Roch space associated to a divisor on a curve. So divisors is a formal sum of points on your curve with some integral coefficient. Almost all of them are zeros. And the Riemann-Roch space, L of D, associated to D, is the vector space, that's the important word, of function whose zeros and poles are controlled by D. So once you have this vector space of function that you can evaluate at the rational points on your curves, you are in business. You just take function in the Riemann-Roch space, you evaluate them at the n distinct rational points on your curve. This will give you an evaluation map. You take the image, and this will give you an algebraic geometry code. And why are we interested in these codes in the hemimetric? Well, first of all, because they have good parameters. So with respect to the singleton bound, they are at most a distance g being the genus of your curve. And they can be longer than the Reed-Solomon codes. You know from previous talk, from Tuesday morning, that algebraic curves respect several bounds on the number of the rational points, and the Servail bound, as I wrote it, tells you that you can go up to q plus 1 plus 2 times g times the square root of q. So if you take maximal curves or almost maximal curves, well, you can construct a code over fq, which will be longer than q. Okay, so we want to mimic that in the Samra metric. Let me give you a little bit more of details in this context, so in the classical context. So I'm fixing a curve x of genus g. I need to work with the rational function that I can evaluate at the points on my curve. So k will be the function field of my curve. And to any points on my curve, I can associate a valuation map, which will, when you apply it to a function in the function field, will give you m, a positive m, if the point is at 0 of your function of multiplicity m, will give you a negative m if the point is a pole of multiplicity m of your function, or will give you 0 if is none of the two. This is exactly the things that allows you to construct the Riemann-Roch space, because this is actually what will enable you to control zeros and poles of your function. So the Riemann-Roch space is a vector space of function whose valuation at p plus np, so the integral coefficient appearing in your divisor d at the place p, is bigger or equal than 0. This is the Riemann-Roch space that you use to construct AG codes, and you can bound the dimension of such space thanks to the Riemann-Roch theorem, or in this context, I will content myself with Riemann's inequality, telling you that this dimension is bigger than the degree of d plus 1 minus the genus of the curve. Okay, so now we want to translate this in the sum-rank metric context. So far, when we went to the sum-rank metric, we were using an extension of finite fields, fq to the r over fq. Now, in this context, I'm going to consider an extension of function field. So I take two curves, x and y, with function field over fq, x and y defined over fq with function field L and k, and I consider pi to be a Galois cover of y over x, which I suppose to have cyclic Galois group of order r. And I take phi, again, to be the generator of the Galois group of the extension L over k, right? Now, for any place on the curve that I have below, I will have one or several but finite number of places in the curve above, which are above my place P. And I am in a Galois extension context. So when I consider the completion of the function field of the curve above at all the places q above just one singular place, well, then they are all isomorphic. They are conjugated by phi. And so I will consider L of p, so this notation, to be the product of the L of q, so the completion of L of q for all the q above a place p. So that's the setting, which is very general. I will, for the rest of the talk, I will just stick to a particular but still very interesting case where I will take y to be that guy. So to ensure that pi is a ramified. So what are the objects that we are going to evaluate to construct our codes, our AG codes in the summary metric. Of course, other polynomials are going to play a role. Now you learn it. And so what I'm going to take is other polynomials with coefficients in the function field of my curve. So L of t of phi here. I'm going to fix a non-zero function in the function field of the curve below, and I'm going to construct this algebra dl of x just by taking polynomials with coefficient in L, quotienting by the polynomial t to the r minus x, which lives in the center of my polynomial ring, my polynomial algebra. Okay, so objects here are not very scary. They are polynomials in T. The coefficients are just function in the function field, and their degree is at most r minus 1. That's all. And I can consider the same things also with coefficients in L of p, which I define here. Same things, polynomials with coefficients which are functions. Okay, if I want to construct codes from curves using this algebra, what will I need? Well, we need our favorite vector space on curves, so Riemann-Roch space, but in our context. And we have seen to define the Riemann-Roch space, I need valuation. Next step, I want to be able to bound the dimension of my Riemann-Roch space, so I will need sort of Riemann's inequality, but in my context. And then you want to evaluate your elements in the Riemann-Roch space at your points. And here is maybe a little less obvious what this evaluation will look like for this polynomial. So let's do this together. First thing, so let us for now just thinking about one place P. So I have several Q places above. I fix one, Qj. So I define a map that goes from my algebra, the L of P of x, into Z over R. So elements here, again, as I said, are polynomials of degree at most r minus 1 with coefficient which lives in L of P, okay? So of course, when you want to define a valuation of a sum, you will define it at least as minimum of something. And the other things that you should have in mind is that you would like the valuation of t to the r to be equal to the valuation at p of x, because t to the r is exactly x. So what we are going to do here is that we define this valuation to be the minimum from I going to 0 to r of the valuation at the place qj of f of fi, and then plus I times the valuation at p of x divided by r. So this defines a valuation with, let's say, valuation not really, but very close to. And the only things that you should be aware of is that, of course, this is not integer. This is clearly by the shape that we have here. And so it will have a denominator which will be at most r, but I will call it bp, meaning that the denominator will depend on whether these terms here are factors in some way. So if I can reduce those two things, then here I will have a denominator which will be smaller than r. Now we'll call it bp. So this is where my valuation will live. Once you have a valuation, the definition of the Riemann-Roch space goes easily, right? You take a divisor in your curve above. The only thing that you have to take care of is that now your coefficients should not be in Z. They should be in Q, more particularly in Z over BP for all the BP. And now you define your Riemann-Roch space associated to this divisor E to be the vector space of elements in D L of x, such that for any place Q, the valuation that we just defined of f plus the coefficients in E of your place is bigger or equal than 0. Exactly in the same way. It can be a little bit scary, but the nice feature of this new Riemann-Roch spaces is that you can indeed look at it as a sum of classical Riemann-Roch space, L of EI, for some explicit EI. So this now is classical Riemann-Roch space that we know how to deal with. And so this is just the direct sum of some Riemann-Roch spaces with divisors living in Y. So now I can just use the Riemann's inequality that I know for all my classical Riemann-Roch space, applying it R times, getting a Riemann's inequality for my new Riemann-Roch space. So I'm going to apply it R times. You need some technical lemma relating the degree of your EI to the degree of E, but that's not very interesting. So you just apply R times the Riemann-Roch space, the Riemann inequality to those Riemann-Roch space, getting a Riemann's inequality for your curves. So we are almost done. We just need valuation at our rational place. That's the last thing to construct the curves. So we have been sweating a little bit, but we are almost there. OK, let us do it at one place. So I fix a rational place in my curve, P, supposing that it does not belong to the image of the support of my divisor. If you know, you know. I mean, this is a classical hypothesis also when you construct AG curves from curves in the classical setting. Let me fix TP to be a uniformizer of my place. And now, so from the beginning, we fix X to be in the function field of the curve below. And I will put some hypothesis on X. So I need it to be a norm of some UP living in LP. So there are some sufficient conditions that you can put to ensure this. I'm not going to enter into this. But you need X which satisfy this condition over here. Once you have that, you're in business. You can define the valuation at P in the following way. You take your Riemann-Roch space, and you evaluate an element here at UP phi. This is very similar to what we did for Reed-Solomon codes. We were evaluating at multiple of phi. And so this will give you, of course, a morphism of what? Well, those elements here have positive valuation at the P, because I'm taking P which are not in the support of E. So those are regular functions in my L of P. So this FU of P phi will exactly define a morphism inside here. Now I'm taking the reduction modulo, the uniformizer. This OKP, since P is rational, OKP, when you reduce by TP, will just be FQ. And these things now, this will really depend on how the place above P behave, but will be some algebra that they will denote by VP. Once you have that, you just do it for S place, and you have your multi-evaluation map, sending an element in the Riemann-Roch space to a vector. All good. To a vector whose entries are FQ linear morphism of VPI. That's a sign, I guess. Yeah, OK. So now when you have a multi-evaluation, you can define your linearized algebraic geometry codes as the image under this evaluation of this new Riemann-Roch space. And you want to study the parameters of those codes. As usual, we already have several tools to do so, because the dimension is, again, just obtained by using the Riemann's inequality. And the only things, as usual, which requires a little bit more work is the minimum distance of your curve. To obtain this bound, you will need another hypothesis. So there are some hypotheses here that will ensure you that X behaves well. And then you also want the algebra that you are using to have non-zero divisors. These will play a central role. How do you prove this bound on the minimum distance? Well, again, you are using the reduced norm in the algebra, because every time that you apply the reduced norm to an element in your algebra, it will give you an element in the center. So in our case, which will live specifically in the function field of our curve. So once you can prove that the dimension of the kernel of this morphism is bounded by the evaluation at P of the reduced norm of F, here you can use all the classical theory, because this is something that lives in the function field of your curve. You just want to put this in a classical Riemann-Roch space and use classical tools to bound this quantity. OK, so now that you have linearized AG codes, just a couple of sanity checks concerning AG codes. First thing, if you take x and y to be the projective line, you retrieve linearized Reed-Solomon curves. As in the Hamming metric, when you take the projective line, you have Reed-Solomon curves. So good. And our bounds tells you that those curves are optimal. Again, we already knew that, of course. And also, asymptotically wise, those curves are good. In the sense that you have an equivalent of the Gilbert-Bachelot bound for the Sambra metric. And again, by using good towers of curves which attain the Yara bound, you can prove that our curves also beat the asymptotic Gilbert-Bachelot bound in the Sambra metric. That's just a sanity check. Let us finish this talk with some open question and work in progress. So in this talk, we have been seeing that we can construct evaluation curves, specifically Reed-Solomon, Reed-Muller, and AG curves that we knew in the Hamming metric, also in the Sambra metric, and that those curves behave in a similar way. They respect similar bounds for the parameters. What's next? Yeah, I understand. I have 5 minutes. I will stop. Well, of course, once you have codes, you want to decode them. So for linearized Reed-Solomon codes, this was done by Martínez-Peñas and improved by some other authors after that. For linearized AG codes, we are working on that with Xavier and with Fabrice Drain, which is with our PhD student. And for linearized Reed-Muller codes, we are not working on that. Feel free to go. But we show that the linearized Reed-Muller codes can be embedded in some linearized AG codes. So a decoding algorithm for linearized AG codes will potentially give you a decoding algorithm for linearized Reed-Muller codes. But yeah, I think that's something that we can do here. This construction of linearized AG codes seems very theoretical. We went through it a little bit fast. But so we are trying to give good explicit construction of those codes with Peter Bielen and Nina Gruitza and Maria Montanucci at DTU. Two of the three were here at the GCT, are here at the GCT. And then you can also think about, well, maybe there are some other construction in the Hamming metric that you would like to generalize. For instance, why not thinking about Coppa codes? And I'm trying to work this out with Pranav Trivedi at Berkeley University. So I will stop here. We'll take your question. And in the meantime, I thank you for your attention.
Are there questions?
Thank you for your talk. You probably know what I'm going to ask. Is there any sense in which substructures in your geometric objects might give rise to desirable properties like locality or something like that, where you might have sort of useful substructures?
There you go. OK, so I would say that the first answer is, what is the definition of local properties in the Sambra metric? And then once you have that, probably yes. I mean, we saw how those codes, in a certain sense, behave well, as in the Hamming case. So why not hope that this will extend to other properties? But yeah, that's just a hope. Thanks for the question.
Other questions?
thank you for the talk. Following more or less the same thing. For example, for AG codes that are, for example, cyclic, we don't know yet if they are asymptotically good or not. And so maybe, I don't know if you already think about this, adding more properties or asking more properties to try to see if the parameters behave well in this case?
Thanks for the question. So far, no, because indeed, I mean, the first question that we had in mind when we finished this is, what about the dual of this code? So that was the first question that we had in mind, and this is what we are working on, because when you want to decode LAG codes and you have in mind stitch not decoding algorithm, you want to know what's the dual. So that's the next question that we are working on. So maybe this will come after that.
Thank you for your talk. I wondered about these LRM codes. If you just apply this for one variable, do you just get LRS codes?
Yes.
So this.
I think so.
So this evaluation in a constant times phi must be hidden in your gammas then, somehow.
Indeed, because gamma give you an element of fq to the r. So basically, you are. But you want some more property.
Right.
But yes, it is. You are basically sending this to some elements of fq to the r times phi,
right.
Respecting some more properties. But so if you write down explicitly gamma, so this will be sort of like you have to fix a generator of fq to the r, and then your gamma u, you can, for instance, take the generator over phi to the power of e times your u of alpha. And then this will also give you back the condition on the pairwise distinct norm, I think.
Mm-hmm. Okay, yeah, it's clear. Thank you.
Other questions?
Kind of answered, but I was going to ask you about the duals of this course.
Mm-hmm.
Are duals of LRM also LRM?
So the question is, so in the Hamming case, the dual of an AG code is an AG code from the same curve. So I guess that's where the question came from. So it is the same for linearized algebraic geometry codes. So we are looking at that. So far we define, let's say, differential linearized AG codes. So we work with the differential. We define residues at that. And so those are, again, linearized AG codes. And then, yeah, so we are still checking the details, but so far the answer will be yes.
Other questions? Okay, so
so since there are no more questions, I will take advantage of you for 2-3 minutes, the last one. So first of all, I hope that you are all excited about codes in the sum rank metric and in the rank matrix. So you may want to come in Bordeaux on February 23-27 for this opera workshop, Open Problems on Rank Metric Codes, which I am organizing with Gianni Alfarano, Martino Borello, and Ferdinando Zullo. And one of the speakers of this conference is here and gave a fantastic talk today, so giving you even more motivation to come. And this workshop will be explicitly conceived for a young researcher, postdoc, and a PhD student. We will be working on projects proposed by the speakers during the whole week. So please consider attending it. And 1 more minute. I've been thinking a little bit about this, but I guess I will give it a try. I just want to mark the point that this is an historical edition of AGC2. Is the first edition, and for me, the first conference in which all the plenary speakers are women. Many of us noticed that. We have been talking about it. We were very happy about it. And yeah, I think that's very important. So I will particularly like to thank the organizers of this edition to have done this first step towards closing the gender gap for future generations. Thank you very much.